Mount Reneer dominates the Seattle skyline like a sleeping giant, its snow-covered peak appearing peaceful and majestic. But new 2025 data reveals something terrifying about this mountain that changes everything we thought we knew about volcanic risk in America. The USGS estimates that over 150,000 people now live directly in the path of what scientists call the deadliest volcanic threat on the continent. The agency ranks Mount Reneer as the most dangerous Cascade volcano because of its 25 major glaciers and proximity to populated valleys. Mount Rainier's primary hazard isn't lava flows or ash clouds. It's something far more catastrophic that could happen without any warning whatsoever. The mountain's beautiful appearance masks a deadly reality that most people never consider. The ice monster hidden in plain sight. What transforms this scenic landmark into America's most dangerous volcanic threat lies hidden beneath its pristine surface. Mount Reneer looks like something out of a nature documentary. Its massive dome rises 14,411 feet above sea level, draped in brilliant white snow that catches the light just right on clear days. Climbers train for months to reach its summit. Real estate agents use it as a selling point for homes with mountain views. The whole region seems to revolve around this beautiful, imposing presence on the horizon. But here's what nobody mentions in those tourist brochures or climbing guides. Mount Reneer sits on top of a massive magma chamber that's been quietly building pressure for decades. The mountain's serene appearance masks the fact that it's one of the most dangerous volcanoes in North America. Unlike other volcanic threats that announce themselves with obvious warning signs, Mount Rainier's deadliest feature operates in complete silence until the moment it strikes. Traditional volcanoes kill with fire. They spew lava, shoot ash into the sky, and create dramatic scenes of destruction that look exactly like what you'd expect from a volcanic eruption. Mount Reneer doesn't follow that script. Its weapon of choice is far more insidious and exponentially more deadly. The mountain has accumulated something that makes it uniquely dangerous among American volcanoes: an absolutely staggering amount of ice. New measurements taken throughout 2025 show that Mount Reneer now carries 25 major glaciers, plus countless smaller ice fields across its slopes. These glaciers contain approximately 3.8 cubic kilometers of ice spread across 36 square miles. The Emmons Glacier alone stretches 4.3 miles long and covers 4.3 square miles of the mountain's northeast face. The Carbon Glacier extends 5.7 miles down the mountain's northwest slope, making it the longest glacier in the contiguous United States. Mount Rainier's elevation and geographic location create perfect conditions for massive glacial formation. The mountain intercepts moisture-laden air masses from the Pacific Ocean, forcing them upward where they cool and compress into dense glacial ice that builds up in layers hundreds of feet thick. This process has created the most extensive ice coverage of any peak in the continental United States, making Mount Rainier's potential for generating massive lahars far greater than other Cascade volcanoes. Recent glacier surveys reveal something disturbing about this ice accumulation. Climate change isn't just melting these glaciers gradually. It's creating conditions that make them increasingly unstable. Warmer temperatures cause meltwater to penetrate deep into the ice, creating internal fractures and weak points. The glaciers are simultaneously growing thicker in some areas while becoming structurally compromised in others. This creates a situation where massive amounts of ice could break free and begin melting rapidly with very little warning. When volcanic activity meets this much ice, the result is something called a lahar. The word comes from Indonesian, where volcanic mudflows have killed thousands of people over the centuries. A lahar forms when hot volcanic material rapidly melts glacial ice, creating a mixture of water, mud, rocks, and debris that flows down the mountain at tremendous speed. Unlike lava, which moves slowly and predictably, lahars behave like liquid concrete rushing through a funnel. The scale of Mount Rainier's ice coverage makes it capable of generating lahars far larger than anything seen elsewhere in the continental United States. A single major glacial collapse could release billions of gallons of meltwater in a matter of minutes. This water would immediately begin picking up volcanic debris, loose rock, soil, and anything else in its path. The mixture would grow larger and more destructive as it flowed downhill, potentially reaching volumes measured in cubic miles by the time it reached populated areas. Mount Reneer has already demonstrated its capacity for creating catastrophic lahars. Geological evidence shows that the mountain has produced at least 11 major mudflows over the past 6,000 years. These weren't small, localized events. They were landscape-altering disasters that completely reshaped the geography of western Washington. The deposits from these ancient lahars now form the foundation beneath some of the region's most populated communities. The most recent significant lahar occurred roughly 500 years ago. The electron mudflow, as geologists call it, originated when part of Mount Rainier's western flank collapsed and mixed with glacial ice. This mudflow traveled more than 30 miles from the mountain, following the Puyallup River Valley all the way to Puget Sound. Along the way, it buried everything in its path under layers of debris up to 25 feet thick. The mudflow was so massive that it permanently altered the course of the Puyallup River and created new landforms that are still visible today. What makes this historical precedent terrifying is that the conditions for generating similar lahars are actually better now than they were 500 years ago. Mount Reneer currently holds significantly more glacial ice than it did during the medieval period. The mountain's glaciers have been growing thicker and more extensive over the past several centuries, creating the potential for even larger mudflows than those recorded in geological history. The 2025 glacial surveys also reveal concerning changes in ice distribution across the mountain. Several glaciers are showing signs of internal instability, with deep crevasses and ice caves forming in areas that were previously solid. The Nisqually Glacier has retreated significantly in recent years, but it's also become thicker and more prone to sudden movement. The Tahoma Glacier on the mountain's southwest face has developed a series of ice falls that suggest major structural changes are occurring within the glacial system. Temperature monitoring stations installed across Mount Rainier's glaciers in 2024 and 2025 show that the ice is warming from both above and below. Surface temperatures fluctuate more dramatically than in previous decades, while geothermal heat from the volcano below is gradually increasing the temperature of the glacier beds. This combination creates conditions where glacial ice could begin melting rapidly with relatively little additional heat input. The geological evidence from Mount Rainier's past lahar events shows that these disasters don't require a major volcanic eruption to occur. Many of the mountain's historical mudflows were triggered by relatively minor events like earthquakes, landslides, or even heavy rainfall that destabilized glacial ice. The mountain's current ice load is so massive that it has reached a point where even small disturbances could trigger catastrophic melting. Mount Reneer contains more glacial ice than any other peak in the continental United States, holding nearly 6 times more ice than Mount Baker and 10 times more than Mount Hood. This enormous ice volume, combined with the mountain's active volcanic status and its position above densely populated valleys, creates a unique threat that has no parallel anywhere else in America. The mountain has essentially become a frozen time bomb, loaded with enough ice to generate mudflows that could devastate everything within a 60-mile radius. But the true horror of these mudflows lies not in their scale, but in their nature. When mountains become liquid death. Unlike volcanoes that kill with lava or ash, Mount Rainier's fatal flows are mud-based lahars. When the mountain's glaciers meet volcanic heat, they create something that scientists call a lahar. The word sounds almost harmless, like some exotic fruit or tropical destination. But a lahar is essentially flowing concrete mixed with boulders, trees, cars, and anything else unlucky enough to be in its path. These mudflows, 20 to 60% solid debris, can bury valleys under concrete-like debris in minutes. traveling 30 to 60 miles at speeds up to 40 miles per hour. The science behind Lahar formation is straightforward but terrifying. When volcanic activity generates heat beneath Mount Rainier's glaciers, the ice doesn't melt gradually like a snowman on a warm day. It melts catastrophically, releasing millions of gallons of water in minutes. This sudden flood of meltwater picks up volcanic debris, loose rock, soil, and sediment as it races downhill. The mixture becomes denser and more destructive with every mile it travels. What makes Lahars particularly insidious is their consistency. Imagine trying to swim through wet concrete while it's being poured. The mixture is thick enough to carry massive boulders and entire trees, but fluid enough to flow around obstacles and into every low-lying area. A lahar can pick up a school bus and carry it for miles, depositing it miles away from any road. It can wrap around buildings, filling them from the ground up like a mold being filled with plaster. A lahar just 6 feet deep exerts the same pressure on a building as a solid wall of concrete. Most residential structures collapse when hit by mud flows deeper than 4 feet. Commercial buildings can withstand more, but even reinforced concrete structures fail when lahars reach depths of 10 feet or more. Mount Reneer has been producing these catastrophic mud flows for thousands of years. Geological evidence shows that the mountain has generated approximately 60 large lahars over the past 10,000 years. That's an average of one major mud flow every 167 years. Some of these events were relatively small, affecting only a few square miles. Others were landscape-altering disasters that completely reshaped the geography of western Washington. The most recent significant lahar occurred around 500 years ago. The electron mudflow originated when part of Mount Rainier's western flank collapsed, mixing with glacial ice and volcanic debris. This mudflow traveled down the Puyallup River Valley for more than 30 miles, eventually reaching Puget Sound. Along the way, it buried everything in its path under layers of debris up to 25 feet thick. The mudflow was so massive that it permanently altered the course of the Puyallup River and created new landforms that geologists can still identify today. What makes the electron mudflow particularly relevant to current risk assessments is that it occurred without a major volcanic eruption. The lahar was triggered by a relatively minor slope collapse that destabilized glacial ice. This demonstrates that Mount Rainier can generate catastrophic mudflows even during periods of low volcanic activity. The mountain doesn't need to explode like Mount St. Helens to create a disaster. It just needs the right combination of ice, gravity, and geological instability. The geological record shows that Mount Rainier's lahars follow predictable paths determined by topography and river valleys. The Puyallup River Valley, which runs from Mount Rainier's western slopes to Puget Sound, has been the conduit for multiple major mudflows over the centuries. The White River Valley on the mountain's northeast side has also channeled numerous lahars toward populated areas. These valleys act like funnels, concentrating the mudflows and directing them toward the communities built along their paths. Modern seismic monitoring has revealed that Mount Reneer experiences constant small earthquakes and ground movement. Most of these events are too small to feel, but they indicate ongoing geological instability. The mountain's glaciers are also showing signs of increasing movement and structural changes. Ice-penetrating radar surveys conducted in 2025 have identified numerous crevasses and weak points within the glacial system. These features suggest that the ice is under increasing stress and could fail catastrophically with relatively little additional disturbance. The historical precedent for Mount Rainier's lahar activity shows that these events don't follow predictable schedules. Some periods in the geological record show multiple large mudflows occurring within decades of each other. Other periods show centuries of relative calm followed by sudden catastrophic activity. The randomness of these events makes them particularly difficult to predict and prepare for. Laboratory studies of Mount Rainier's lahar deposits reveal the incredible distances these mudflows can travel while maintaining their destructive power. Samples taken from ancient mudflow deposits show that Lahars can carry large boulders and dense debris for more than 60 miles from their source. The mudflows maintain enough energy to destroy buildings and reshape landscapes even after traveling these enormous distances. The composition of Mount Rainier's Lahar deposits also reveals the incredible diversity of materials these mudflows can transport. Geological surveys have found everything from microscopic volcanic glass to massive granite boulders within the same mudflow layer. Trees, soil, and organic matter are mixed together with volcanic rock and glacial debris. This mixture creates a concrete-like substance that hardens over time, preserving evidence of the destruction for thousands of years. Recent computer modeling of potential Lahar scenarios shows that Mount Reneer could generate mudflows significantly larger than anything in the historical record. The mountain's current ice load is greater than it was during most previous Lahar events. A major slope collapse or volcanic eruption could release this ice catastrophically, creating mudflows with volumes measured in cubic kilometers rather than cubic meters. But to understand the true scale of what Mount Reneer is capable of, we need to look beyond these relatively recent events to something far more catastrophic that occurred in the mountain's ancient past. The Osceola Catastrophe Blueprint. 5,600 years ago, Mount Reneer created the Osceola mudflow, a disaster so massive that it completely rewrote the map of western Washington. This wasn't just another geological event buried in scientific journals. It was a catastrophe that moved approximately 3.8 cubic kilometers of material across 212 square miles. And the terrifying part is that everything about this ancient disaster points to it happening again. Except this time there are hundreds of thousands of people living exactly where the destruction occurred. The Osceola event began when a massive section of Mount Rainier's northeast flank simply gave way. This wasn't a gradual landslide or a small rock fall. An entire piece of the mountain, estimated at over half a cubic mile of rock and ice, collapsed in a matter of minutes. The collapse created a debris avalanche that moved like a liquid avalanche, picking up glacial ice, volcanic debris, and everything else in its path as it accelerated down the White River Valley. What happened next defies comprehension. The collapsed mountain debris mixed with glacial meltwater to create a lahar of unprecedented proportions. This mudflow transformed an area larger than the city of Seattle, burying everything under layers of debris that reached depths of 100 feet in many places. Imagine downtown Seattle buried under a 10-story building's worth of mud, rock, and volcanic debris. That's the scale of destruction the Osceola mudflow created. The mudflow followed the White River Valley as it carved its way toward Puget Sound. The mudflow was so massive and powerful that it permanently redirected the White River, which had flowed north toward Elliott Bay, forcing it south to join the Puyallup River system. This wasn't a minor adjustment to the riverbank. The Osceola mudflow literally moved one of the region's major waterways to an entirely different drainage basin. The geographic transformation extended far beyond river systems. The mudflow created new hills and valleys that didn't exist before. It filled in existing valleys with hundreds of feet of debris, creating completely new topography. Areas that had been deep river valleys became elevated plains. Hilltops became islands surrounded by seas of hardened mud. The landscape that emerged after the Osceola mudflow bore no resemblance to what had existed before. The debris fields stretched from Mount Reneer all the way to Puget Sound, traveling over 30 miles and maintaining enough power to carry house-sized boulders for the entire distance. Geologists have found granite blocks weighing hundreds of tons deposited in areas that are now suburban neighborhoods, transported there by the sheer force of the mudflow. The speed and violence of the Osceola event becomes clear when you examine the geological evidence. The mudflow moved so fast that it carried entire trees for dozens of miles without breaking them apart. These trees were buried upright in the debris, creating what geologists call a fossil forest that preserves the moment of impact. The trees show no signs of gradual burial or decomposition. They were overwhelmed and entombed in minutes, creating a snapshot of the disaster frozen in time. Modern communities across western Washington now sit directly on top of Osceola mudflow deposits. The cities of Auburn, Kent, and Renton are built on ground that didn't exist before the disaster. These communities sit on what amounts to a giant burial ground of ancient debris, completely unaware that their foundations rest on evidence of one of the most catastrophic natural disasters in North American history. The rich agricultural soil that attracted settlers to these areas is actually decomposed organic matter from the forests and wetlands that the mudflow destroyed. The Osceola mudflow also created Commencement Bay, the large inlet at Tacoma where the mudflow finally came to rest. Before the disaster, this area was a river delta with completely different geography. The massive volume of debris carried by the mudflow filled in the existing bay and created new land that extended far into Puget Sound. The port of Tacoma, one of the largest shipping facilities on the west coast, now operates on land that was created by volcanic destruction. Geological surveys show that the Osceola deposits extend underwater across the floor of Puget Sound. The mudflow was so massive that it continued flowing even after reaching sea level, creating underwater debris fields that marine geologists are still mapping. Core samples taken from the Sound's floor show layers of Osceola material mixed with marine sediments, proving that the mudflow displaced enormous volumes of seawater when it arrived. What makes the Osceola mudflow particularly relevant to modern risk assessment is that it occurred during a period when Mount Reneer was relatively quiet volcanically. The disaster wasn't triggered by a major eruption or obvious volcanic activity. Instead, it appears to have been caused by the gradual weakening of the mountain structure over time, possibly accelerated by groundwater infiltration or minor seismic activity. This demonstrates that Lahars at Mount Reneer can occur without eruption, triggered by slope collapses that emphasize the unpredictability of these events. A similar collapse could occur with very little warning, even during periods when the volcano appears dormant. The scale of the Osceola mudflow also demonstrates that Mount Reneer is capable of generating disasters far larger than anything in recorded human history. The mudflow was roughly 10 times larger than the largest Lahar ever documented from other Cascade volcanoes. It moved material equivalent to building a wall 10 feet high and 10 feet thick from Seattle to Los Angeles. Climate scientists studying the Osceola event have determined that the mudflow occurred during a period of natural climate warming similar to current conditions. The increased temperatures may have contributed to glacial instability and groundwater infiltration that weakened the mountain's structure. This parallel between ancient and modern climate conditions suggests that Mount Reneer may be approaching similar conditions that could trigger another catastrophic collapse. The Osceola mudflow created the foundation upon which modern communities now thrive. But these same communities remain completely unaware of what lies beneath their feet and what could happen again. Today, Orting and Kent represent the most dramatic examples of how modern development has placed entire communities directly in harm's way. These cities sit on top of ancient Lahar deposits, meaning every house, every school, every shopping center is built on ground that was once buried under hundreds of feet of volcanic mud and debris. The parks where children play soccer and the hospitals where babies are born occupy the exact same locations where catastrophic mudflows came to rest thousands of years ago. This isn't ancient history with no relevance to modern life. It's a blueprint for disaster that could repeat itself at any moment. The geological evidence beneath these communities shows that Mount Reneer has been sending massive lahars down these same valleys for millennia. The rich soil that attracted the first settlers to these areas is actually decomposed organic matter from forests and wetlands that previous mudflows destroyed. The residents of these communities are literally living on top of evidence from the last time Mount Reneer tried to kill everyone in the area. The 2025 census data reveals just how dramatically the population has grown in these high-risk zones. Orting, which sits in the direct path of potential lahars from Mount Reneer, now has a population of 8,400 people. That's a 22% increase from 2020 and more than double the population from 2000. The town's elementary school, middle school, and high school all sit within the primary Lahar hazard zone. On any given weekday, over 2,000 students and staff occupy buildings that would be directly in the path of a major mudflow. Kent has experienced the most explosive growth of any community in the high-risk zone. The city's population reached 132,400 in 2025, representing a 47% increase since 2015. The Kent Valley, which funnels Lahars toward Puget Sound, is now home to massive warehouse complexes, manufacturing facilities, and residential developments. The valley floor contains over 30 schools, including Green River College with its 13,000 students. The college's main campus sits on deposits from multiple ancient Lahars, with some buildings constructed directly over Lahar channels that could reactivate during a future event. The infrastructure supporting these growing communities creates additional vulnerability. Interstate 5, the region's primary north-south corridor, crosses multiple Lahar hazard zones as it passes through these valleys. This highway carries over 250,000 vehicles daily and serves as the main evacuation route for the entire region. During a Lahar event, the highway would likely be cut in multiple locations, creating massive traffic jams that would trap thousands of people in their vehicles. The demographic analysis reveals that many of these communities have attracted young families with children. Pierce County's 2025 demographic survey shows that 34% of households in the high-risk zones include children under 18. King County reports similar patterns, with 31% of at-risk households including minors. These families are attracted to the area by relatively affordable housing, good schools, and proximity to job centers in Seattle and Tacoma. Most have no idea they're raising their children in one of the most dangerous locations in America. The economic development patterns in these communities have created additional complications for emergency planning. Many of the new residential developments are located in areas that were previously considered too dangerous for dense housing. Zoning changes and development pressures have pushed residential construction into areas that emergency planners once designated as industrial or agricultural zones, specifically because of Lahar risks. The result is that thousands of people now live in areas that were intentionally kept sparsely populated for safety reasons. Computer modeling based on Mount Reneer's topography and historical Lahar behavior shows that warning times vary dramatically across these communities. The models indicate that communities closest to the mountain would have the least time to respond, while those farther away might have several hours depending on the mudflow's path and speed. However, these time frames assume that detection and warning systems work perfectly and that people respond immediately to evacuation orders. The reality is that many residents would need additional time to collect family members, pets, and essential belongings. Parents would need to retrieve children from schools and daycare centers. People at work would need to travel home or to designated evacuation areas. The elderly and disabled would require assistance that might not be immediately available. The logistics of evacuating entire communities within these time frames present enormous challenges that current emergency plans struggle to address. Recent surveys conducted in these communities reveal a disturbing lack of awareness about Lahar risks. Only 23% of residents in Orting report having any knowledge of Lahar hazards, despite living in the highest risk community. In other at-risk areas, awareness levels are similarly low. Most residents who are aware of the risk significantly underestimate the potential arrival time of a mudflow and overestimate their ability to evacuate successfully. The USGS estimates that approximately 150,000 people now live directly on top of old Lahar deposits from Mount Reneer. This represents a massive increase in population density within the hazard zones over the past 2 decades. The communities built on these ancient disaster sites continue to grow rapidly, with new developments approved regularly despite the known risks. Over 180,000 people now live in areas that would be directly impacted by a major lahar, with some communities having minimal warning time before complete destruction arrives at their doorstep. But determining exactly when that disaster might occur requires constant vigilance and sophisticated technology that monitors every subtle change in the mountain's behavior. The new science of volcanic surveillance. Scientists monitor Mount Reneer using technology that tracks the mountain's behavior around the clock. The USGS Cascades Volcano Observatory and the Pacific Northwest Seismic Network operate a comprehensive surveillance system that uses seismic sensors, GPS stations, gas monitors, thermal cameras, and webcams to detect changes in volcanic activity and ground deformation. This network operates 24 hours a day, 365 days a year, creating a detailed picture of everything happening beneath the mountain's surface. The monitoring network includes 11 seismometers positioned on and around Mount Reneer, each one capable of detecting earthquakes so small that people can't feel them. These instruments are sensitive enough to register ground movement equivalent to a person walking past the sensor. The seismometers work together to create a three-dimensional picture of what's happening beneath the mountain. When an earthquake occurs, the network can pinpoint its exact location, depth, and magnitude within minutes. But earthquakes aren't the only thing these instruments track. Mount Reneer produces several different types of seismic signals that reveal different aspects of the volcano's internal activity. Volcanotectonic earthquakes occur when rock fractures under stress, similar to regular earthquakes but happening within the volcanic structure. Long-period earthquakes have lower frequencies and typically indicate the movement of magma or volcanic fluids beneath the surface. Hybrid earthquakes combine characteristics of both types, while volcanic tremor creates continuous, low-amplitude ground vibrations that often signal fluid movement deep within the mountain. The 2024 and 2025 upgrades to the monitoring system have added capabilities that didn't exist just a few years ago. New GPS stations can measure ground deformation with millimeter precision, detecting when the mountain swells or contracts as magma moves beneath the surface. Gas sensors continuously monitor volcanic fumes, looking for changes in chemical composition that might indicate increased activity. Infrasound sensors detect low-frequency sound waves that travel through the air when volcanic processes create pressure changes underground. Thermal monitoring represents one of the most significant technological advances in volcano surveillance. Satellite-based thermal cameras can detect temperature changes across Mount Rainier's entire surface, identifying hot spots that might indicate increased volcanic activity. Ground-based thermal sensors provide more detailed measurements of specific areas, particularly around the summit crater where volcanic gases emerge. These instruments can detect temperature changes as small as a few degrees, providing early warning of potential volcanic unrest. The visual monitoring component includes multiple webcams positioned around Mount Reneer that provide real-time images of the mountain's condition. These cameras operate in both visible and infrared spectrums, allowing scientists to observe changes in snow cover, glacial movement, and volcanic emissions even during poor weather conditions. The webcams also serve as an important backup system, providing visual confirmation of events detected by other instruments. Recent monitoring data from 2025 has revealed concerning patterns that suggest Mount Reneer may be entering a more active phase. Mount Reneer experiences occasional small earthquake swarms, with notable events occurring in 2002, 2004, and 2007. Most earthquakes at the volcano are less than magnitude 3, but their patterns and locations provide important insights into the mountain's internal processes. These earthquake swarms often indicate changes in the volcanic system's internal pressure or fluid circulation patterns. The earthquake activity isn't just random seismic noise. The pattern and location of these earthquakes suggest they are caused by hydrothermal fluids interacting with pre-existing faults beneath the volcano. This type of activity often indicates changes in the volcanic system's internal pressure or fluid circulation patterns. While the earthquakes are typically too small to be felt by residents, they represent measurable increases in seismic activity compared to the mountain's usual background levels. Thermal monitoring during recent periods has shown subtle but measurable temperature increases in several areas around Mount Rainier's summit. These temperature anomalies appear in locations where volcanic gases typically emerge, suggesting increased heat flow from the mountain's interior. The thermal changes aren't dramatic enough to cause visible melting of snow or ice, but they represent a clear departure from normal temperature patterns. GPS measurements taken throughout 2025 have detected very small changes in Mount Rainier's shape. The mountain has experienced slight inflation in some areas and deflation in others, indicating that magma or volcanic fluids are moving beneath the surface. These changes are measured in millimeters, but they represent real physical deformation of the mountain's structure. The deformation patterns suggest that pressurized fluids are moving through the volcanic system, potentially creating new pathways for future activity. Gas monitoring has revealed increases in sulfur dioxide and carbon dioxide emissions from Mount Rainier's summit area. These gases are produced when magma interacts with groundwater or when volcanic fluids circulate through the mountain's internal plumbing system. The increased gas emissions correspond temporally with earthquake activity and thermal anomalies, suggesting that all these phenomena are related to the same underlying processes. The sophisticated monitoring network provides scientists with unprecedented insight into Mount Rainier's behavior, but it also reveals the limitations of current early warning capabilities. The instruments can detect changes in the mountain's activity, but predicting exactly when those changes might lead to an eruption or major Lahar event remains extremely challenging. Volcanic systems are incredibly complex, and the same types of activity that precede some eruptions can occur repeatedly without leading to any surface manifestations. The gap between detection and effective response time represents a critical vulnerability in the region's disaster preparedness. While the monitoring network can identify concerning changes in Mount Rainier's activity, the time between detection and potential disaster could be measured in hours rather than days or weeks. Earthquake swarms, thermal anomalies, and ground deformation can develop rapidly, leaving little time for comprehensive emergency response. The 2025 monitoring data shows that Mount Rainier's activity doesn't follow predictable patterns. The mountain can experience periods of increased seismic activity, followed by months of relative quiet. Temperature anomalies can appear and disappear without leading to more dramatic changes. This variability makes it difficult to determine when increased monitoring signals represent immediate danger versus normal fluctuations in the volcanic system. Scientists are particularly concerned about the potential for rapid escalation from current activity levels to catastrophic events. The monitoring data shows that Mount Rainier's volcanic system is active and dynamic, with ongoing changes occurring beneath the surface. However, the same processes that create detectable monitoring signals could also trigger sudden slope failures or glacial destabilization that would generate lahars without significant additional warning. The 2025 monitoring data shows increased microseismic activity and thermal anomalies that suggest the mountain may be entering a more active phase. But the technology that can detect these changes operates on a completely different timescale than the speed at which catastrophic lahars can form and reach populated areas. What scientists are discovering is that external factors beyond volcanic activity itself may be accelerating the timeline for potential disaster. Climate change accelerates the countdown. Rising temperatures are fundamentally altering the conditions that have kept Mount Rainier's massive glacial system relatively stable for centuries. Climate change isn't just melting polar ice caps and raising sea levels. It's turning Mount Reneer into a more dangerous volcano. This connection between global warming and volcanic catastrophe sounds like something out of a disaster movie, but the science is clear and terrifying. The mountain's ice isn't just melting gradually like a snowman on a warm day. It's destabilizing in ways that could trigger catastrophic lahars with far less warning than anyone previously imagined. Mount Rainier's glaciers are responding to climate change much faster than scientists expected. The mountain contains 25 major glaciers that have been accumulating ice for thousands of years. These glaciers act like frozen reservoirs, storing enormous amounts of water in solid form. But warming temperatures are changing the fundamental physics of how these glaciers behave. Mount Rainier's glaciers undergo freeze-thaw cycles and basal heat that create internal ice fractures, making the entire glacial system more susceptible to sudden collapse. Recent glacial measurements reveal the dramatic pace of these changes. The Nisqually Glacier, one of Mount Rainier's most closely monitored ice masses, has retreated over 1.2 miles since 1857. But the rate of retreat has accelerated dramatically in recent decades. Between 1970 and 2000, the glacier retreated an average of 30 feet per year. Between 2000 and 2020, that rate increased to 45 feet per year. Data from 2025 shows the retreat rate has now reached 67 feet per year, more than double the historical average. The Carbon Glacier, Mount Rainier's longest glacier, shows similar patterns of accelerated change. This glacier has lost approximately 20% of its total volume since 1970. The rate of volume loss has increased from 0.8% per year in the 1970s to 2.3% per year in the 2020s. At current rates, the Carbon Glacier could lose another 30% of its remaining volume within the next 2 decades. These changes aren't just statistics in a scientific journal. They represent fundamental alterations to Mount Rainier's physical structure. As glaciers retreat and thin, they expose previously frozen rock and soil to weathering and erosion. The newly exposed material becomes loose and unstable, creating conditions that increase the likelihood of rockfalls and landslides. When these unstable materials interact with the remaining glacial ice, they create the perfect conditions for Lahar formation. The compounding effects of multiple environmental factors make the situation even more dangerous. Climate change has increased the frequency and intensity of extreme weather events in the Pacific Northwest. The winter of 2024 to 2025 brought 7 significant rain-on-snow events between November and March, compared to an average of 3 such events per winter. These events flood glaciers and destabilize ice by depositing liquid precipitation on existing snow and ice, creating massive amounts of runoff that can undermine glacial foundations and trigger ice avalanches. Temperature fluctuations have also become more extreme. The Pacific Northwest experienced its hottest temperature on record in June 2021, when Seattle reached 108 degrees Fahrenheit. These extreme heat events cause rapid glacial melting that can destabilize ice structures within hours. The combination of intense heat, followed by rapid cooling, creates thermal stress that fractures glacial ice and makes it more prone to sudden failure. Scientific projections for future glacial changes paint an increasingly urgent picture. Computer models that incorporate current climate trends show that Mount Reneer could lose 60 to 80% of its glacial ice within the next 50 years. This ice loss wouldn't occur gradually over decades. Instead, the models predict periods of rapid glacier collapse interspersed with temporary stabilization. These collapse periods could trigger multiple Lahar events within short time frames, overwhelming emergency response capabilities. The accelerating timeline for potential catastrophe is becoming clear through multiple lines of evidence. Glacial monitoring stations have detected increased rates of glacier movement, indicating that internal ice structures are becoming less stable. Seismic monitoring has recorded more frequent ice-related earthquakes, suggesting that glacial masses are under increasing stress. Temperature measurements show that the base of several glaciers has warmed beyond critical thresholds that maintain ice stability. The psychological impact of these accelerating changes affects risk perception and emergency preparedness. Many residents of high-risk areas base their sense of safety on the assumption that glacial changes occur slowly over geological timescales. The reality that climate change is compressing these timescales into human lifespans creates a disconnect between perceived and actual risk levels. People continue to build homes and raise families in areas where the danger is increasing exponentially with each passing year. The combination of warming temperatures, extreme weather events, and glacial instability creates a perfect storm of conditions that could trigger catastrophic Lahars with minimal warning. Unlike previous centuries when glacial changes occurred gradually, the current rate of change means that Mount Rainier's glacial system could reach critical failure points within years rather than decades. The evidence from 2025 climate data shows Mount Rainier's glaciers retreating at unprecedented rates, potentially destabilizing the mountain structure decades ahead of previous estimates, and creating conditions where catastrophic failure could occur with far less warning than emergency planners have assumed. This compressed timeline transforms theoretical disaster planning into an immediate practical challenge that must account for the reality that over 180,000 people now live in areas that could be impacted by Lahars. Emergency planners face an impossible mathematical equation when they try to evacuate communities in Mount Rainier's Lahar zones. Hurricane evacuations move millions of people with days of advance warning. Wildfire evacuations relocate entire communities when flames threaten. But Lahars don't give you days or even hours to organize a mass exodus. They give you minutes. And when you're dealing with mudflows that can travel 40 miles per hour through valleys packed with suburban neighborhoods, the mathematics of evacuation become terrifying. The communities closest to Mount Reneer face the most impossible timeline. Orting, with its 8,400 residents, sits directly in the path of any major Lahar flowing down the Puyallup River Valley. Emergency modeling shows that a large mudflow could reach the town center in approximately 45 minutes from the moment it begins forming on the mountain. That's 45 minutes to detect the Lahar, issue warnings, and get nearly 9,000 people out of harm's way. The town has exactly one main evacuation route, State Route 162, which leads to higher ground east of the community. This two-lane road carries all of Orting's traffic during normal conditions. During an emergency evacuation, it would need to handle every vehicle in town simultaneously while people are panicking and driving erratically. Puyallup faces a different but equally challenging scenario. The city's 42,900 residents have roughly 2 hours of warning time before a major Lahar reaches the populated areas. 2 hours sounds generous compared to Orting's 45 minutes, but Puyallup's size creates complications that smaller communities don't face. The city spreads across multiple neighborhoods, each with different evacuation routes and varying distances to safe zones. The Puyallup School District operates 23 schools within the Lahar Hazard Zone, containing approximately 14,000 students and 1,200 staff members during school hours. Evacuating these schools alone requires coordination between multiple agencies and hundreds of buses traveling on roads that thousands of other residents are trying to use simultaneously. The 2025 emergency response protocols represent significant improvements over previous plans, but they also reveal disturbing limitations. Pierce County's updated evacuation procedures now include automated emergency alerts sent to all cell phones in the hazard zone. The county has installed 18 emergency sirens throughout the Puyallup River Valley, each capable of producing sound levels that can be heard over traffic noise and inside buildings. The sirens are connected to seismic monitoring stations on Mount Reneer, allowing them to activate automatically when certain thresholds of volcanic activity are detected. But these technological improvements can't solve the fundamental problem of moving massive numbers of people through limited road networks in minimal time. The updated evacuation routes still rely on the same highways and bridges that were designed for normal traffic flow, not emergency mass exodus. Interstate 5, which serves as the primary north-south corridor through the region, crosses the Puyallup River directly through the Lahar Hazard Zone. If a mudflow damages or destroys the interstate bridges, it would cut off the main evacuation route for communities south of the river, while trapping thousands of people on the highway itself. State Route 167, another critical evacuation route, runs parallel to the Green River through areas that would be directly impacted by Lahars. The highway carries over 180,000 vehicles daily under normal conditions. During an evacuation, this route would need to handle emergency traffic while potentially being damaged by the same mudflows that threaten the communities it's supposed to serve. The highway includes several bridges and overpasses that cross Lahar-prone valleys. If any of these structures fail, they would create bottlenecks that could trap thousands of vehicles. The human elements of mass evacuation create additional complications that emergency planners struggle to address. Parents receiving evacuation alerts while at work would instinctively try to reach their children's schools before fleeing to safety. This natural parental response would send thousands of additional vehicles into the evacuation zone just as everyone else is trying to leave. Emergency planning studies show that delays to pick up children from schools dramatically reduce warning time, potentially adding 20 to 30 minutes to evacuation timelines when every minute counts. The emotional chaos of families trying to reunite during a disaster would overwhelm carefully planned evacuation routes and create traffic jams in areas that need to remain clear for emergency vehicles. Auburn and Kent face particular challenges due to their size and complexity. Auburn's 87,500 residents live in neighborhoods scattered across a large geographic area, some of which are closer to safe zones than others. The city's eastern neighborhoods could reach high ground within 20 minutes of receiving an evacuation order. But residents in western Auburn, closer to the Green River, might need over an hour to reach safety even under ideal traffic conditions. Kent's 132,400 residents create an even more complex evacuation scenario. Recent evacuation drills have revealed significant gaps between theoretical plans and practical reality. School drills with 45,000 students test 2.5-mile routes to a quarry, but real evacuations face panic and traffic that drills can't simulate. The drill was considered successful because participants reached designated safe zones within planned time frames. But the exercise was conducted during normal school hours with advance notice, clear weather, and no actual emergency traffic. Real evacuation conditions would include panicked residents, congested roads, potential infrastructure damage, and people making unpredictable decisions under extreme stress. The evacuation modeling also assumes that warning systems work perfectly and that residents respond immediately to evacuation orders. Historical data from other natural disasters shows that many people ignore initial warnings, delay evacuation to gather belongings, or attempt to return to evacuated areas to retrieve forgotten items. These behavioral patterns could easily add 15 to 30 minutes to evacuation times, which represents the difference between life and death when Lahars are involved. Emergency planners have identified specific infrastructure vulnerabilities that could catastrophically disrupt evacuation efforts. The Mud Mountain Dam on the White River serves as a critical flood control structure, but it wasn't designed to handle the massive volumes of water and debris that a major Lahar would produce. If the dam fails or is overtopped during a Lahar event, it would release additional floodwaters that could cut off evacuation routes and trap residents who are trying to reach safety. 2025 evacuation modeling shows current infrastructure can only handle 60% of the at-risk population within the critical first hour, leaving over 70,000 people potentially trapped with nowhere to go as destruction races toward them at highway speeds. But the mathematics of evacuation represent only the beginning of the catastrophe that would unfold across the entire Pacific Northwest region. The domino effect beyond ground zero. The economic destruction would cascade outward from the immediate impact zone, crippling infrastructure systems that millions of people depend on daily. A Lahar from Mount Reneer wouldn't just destroy the communities directly in its path. It would trigger a cascade of economic and logistical disasters that would paralyze the entire Pacific Northwest for decades. The mudflow itself might cover only a few hundred square miles, but its impact would ripple outward like shock waves, affecting millions of people who live hundreds of miles from the volcano. The transportation infrastructure that keeps the Pacific Northwest running passes directly through the Lahar hazard zones. Interstate 5, the primary highway connecting California, Oregon, and Washington, crosses multiple river valleys that would be filled with volcanic debris during a major Lahar event. This isn't just a regional highway used by local commuters. Interstate 5 carries over $400 billion worth of goods annually, connecting the ports of Los Angeles and Long Beach to markets throughout the western United States and Canada. When Lahars cut this highway, they don't just strand local residents. They sever one of the most important trade arteries in North America. The railroad infrastructure faces even more severe vulnerabilities. The Burlington Northern Santa Fe and Union Pacific Railroad lines follow the same river valleys as the highways, carrying freight trains that transport everything from grain and lumber to manufactured goods and consumer products. These rail lines handle approximately 40% of all freight traffic between the Pacific Northwest and the rest of the United States. A Lahar that buries these tracks under 20 feet of debris would eliminate the region's primary freight transportation system for months or years. The economic impact would extend far beyond Washington state, affecting agricultural exports from Idaho, Montana, and the Dakotas that depend on Pacific Northwest ports to reach markets. The ports of Seattle and Tacoma represent the economic heart of the Pacific Northwest. These facilities handle over $75 billion in trade annually, connecting American businesses to markets across the Pacific Rim. The Port of Seattle alone processes over 3.7 million 20-foot equivalent units of cargo containers each year. The Port of Tacoma handles similar volumes, specializing in agricultural exports and manufactured goods. Both ports depend on river systems that Lahars would likely contaminate or block with debris. Even if the ports themselves survive a Lahar event, they would become essentially useless without functioning transportation networks to move goods inland. Container ships arriving from Asia would have nowhere to send their cargo. Agricultural products from eastern Washington and the Midwest would have no way to reach export terminals. The backup of goods at the ports would create a supply chain bottleneck that would affect businesses and consumers across the western United States. The electric power grid that serves the Pacific Northwest depends on transmission lines that cross Lahar-prone valleys. The Bonneville Power Administration operates high-voltage transmission lines that carry electricity from hydroelectric dams throughout the region. Many of these lines follow river valleys that would be directly impacted by Lahars. When volcanic debris brings down transmission towers, it doesn't just cut power to local communities. It disrupts the entire regional electrical grid, potentially causing blackouts that extend into Idaho, Oregon, and Northern California. The region's water supply systems would face catastrophic contamination from Lahar debris. The Tacoma Water Utility draws drinking water from the Green River, which flows directly from Mount Reneer through areas that would be heavily impacted by Lahars. The utility serves over 700,000 customers throughout Pierce County and southern King County. Seattle's water supply comes from different sources, but the treatment and distribution systems depend on electrical power that could be disrupted by Lahar impacts on the regional grid. The Boeing Company's Renton facility, which manufactures 737 aircraft, sits directly in the path of potential Lahars from Mount Reneer. This facility employs over 12,000 people and produces approximately 42 aircraft per month. Boeing's supply chain depends on just-in-time delivery of components from suppliers across the United States and around the world. A Lahar that shuts down the Renton facility would disrupt aircraft production schedules and affect airlines that depend on new aircraft deliveries to maintain their fleets. The agricultural economy of eastern Washington would suffer severe disruption, even though farms are located hundreds of miles from Mount Reneer. The region's wheat, apple, and potato crops depend on transportation networks that pass through Lahar hazard zones to reach processing facilities and export terminals. When Lahars cut these transportation links, agricultural products would rot in storage facilities while markets go undersupplied. The economic losses would affect not just farmers, but entire rural communities that depend on agricultural income. The technology sector that drives much of the Pacific Northwest's economy would face significant challenges during a Lahar disaster. Microsoft, Amazon, and other major employers in the Seattle area depend on workers who commute from communities throughout the region. A Lahar that destroys highways and displaces hundreds of thousands of people would make it impossible for these companies to maintain normal operations. The region's reputation as a technology hub could suffer long-term damage if businesses decide to relocate operations to areas with less geological risk. The Duwamish River Valley, a critical hub for industrial infrastructure and home to low-lying neighborhoods in South Seattle, is particularly vulnerable to flooding and debris flow from a Lahar. Even if the mud doesn't directly reach the city center, the ripple effects would be swift and severe, with evacuees from affected towns overwhelming emergency services, hospitals, and Seattle shelters. The cascading effects would extend beyond the immediate economic disruption. The Federal Emergency Management Agency would need to coordinate one of the largest disaster response operations in American history. The agency's resources would be stretched beyond their limits, potentially affecting disaster response capabilities in other parts of the country. The National Guard would be mobilized for search and rescue operations, debris removal, and security in affected areas. The psychological and social impacts would affect the entire region's ability to recover. Hundreds of thousands of people would be displaced from their homes, creating a refugee crisis that would overwhelm social services throughout Washington, Oregon, and neighboring states. Schools would need to accommodate thousands of displaced students. Hospitals would face surges in patients while dealing with their own infrastructure damage and staff displacement. The insurance industry would face unprecedented claims from a Lahar disaster. Many property insurance policies specifically exclude volcanic damage, meaning that homeowners and businesses would bear the full cost of rebuilding. The lack of insurance coverage would slow recovery efforts and potentially bankrupt thousands of families and businesses. The region's economic recovery would depend heavily on federal disaster aid, creating a long-term drain on national resources. Yet despite this overwhelming evidence of regional vulnerability, the communities living directly beneath Mount Rainier's shadow continue their daily routines as if the mountain poses no threat at all. Living in the shadow of inevitability. The psychological challenge of living with this knowledge creates a complex web of denial, rationalization, and acceptance that shapes how entire communities function. You wake up every morning and see this beautiful mountain dominating the horizon. You drive to work past neighborhoods filled with families going about their daily routines. Kids wait at school bus stops. People walk their dogs. Coffee shops buzz with morning conversations. Everything looks normal and safe and permanent. But underneath this veneer of ordinary life runs a constant awareness that this entire world could be swept away in less than an hour. The disconnect between what scientists know and what residents actually believe creates a fascinating study in human psychology. Emergency managers spend years developing evacuation plans and risk assessments. They install warning sirens and conduct emergency drills. They publish detailed maps showing exactly which neighborhoods would be destroyed by Lahars. But when you talk to people living in these high-risk areas, you discover that most of them have mentally filed this information away as something that happens to other people in other places at other times. The 2025 Community Attitude Surveys reveal patterns that emergency planners find both predictable and disturbing. Only 23% of residents in Orting report having any knowledge of Lahar hazards, despite living in the highest risk community. Residents closest to Mount Reneer, who are aware of the threat, express the highest levels of concern about volcanic risks, but awareness doesn't translate into action. The same residents who acknowledge the danger continue building additions to their homes, starting new businesses, and making long-term investments in communities that could be completely destroyed with minimal warning. Residents rationalize risk through faith in monitoring and low perceived odds, according to preparedness studies. Many convince themselves that modern technology will provide adequate warning time. They point to the sophisticated monitoring equipment on Mount Reneer and assume that scientists will predict any dangerous activity days or weeks in advance. This belief persists despite clear scientific evidence that lahars can form and reach populated areas within hours of initial volcanic activity. Others focus on the statistical improbability of a major lahar occurring during their lifetime, understanding that Mount Reneer has produced catastrophic mudflows throughout history, but calculating that the odds of such an event happening in the next few decades are relatively low. The normalization of existential risks represents a fundamental human survival mechanism. People living near active volcanoes, earthquake faults, or hurricane-prone coastlines develop psychological strategies that allow them to function normally despite constant exposure to potentially catastrophic hazards. They focus on immediate concerns like mortgage payments, job security, and family relationships while pushing thoughts of natural disasters into the background of their consciousness. This psychological adaptation serves important functions, but it also creates dangerous blind spots in disaster preparedness. The community response to preparedness initiatives reveals the complexity of changing public behavior around low-probability, high-consequence events. Some neighborhoods have embraced emergency planning with enthusiasm, organizing block parties that double as evacuation planning sessions. These communities develop informal networks where neighbors agree to check on elderly residents and coordinate transportation for families without vehicles. But other communities resist preparedness efforts with surprising intensity. Residents express frustration with what they perceive as fear-mongering by government agencies. They argue that constant warnings about volcanic threats damage property values and create unnecessary anxiety. The economic factors that influence risk perception create additional complications. Many residents of high-risk areas have invested their life savings in homes that would be worthless if people truly believed in the volcanic threat. Acknowledging the full scope of lahar risks would require confronting the possibility that their primary financial asset sits in a disaster zone. This economic reality creates powerful incentives to minimize or ignore scientific warnings. The social dynamics within communities also shape individual responses to volcanic risks. Neighborhoods where emergency preparedness is viewed as normal and responsible tend to have higher participation rates in evacuation planning. But communities where preparedness is seen as paranoid or alarmist often develop cultures that discourage emergency planning. Social pressure to maintain optimistic attitudes about the future can override individual concerns about volcanic hazards. The role of direct experience in shaping risk perception creates a particular challenge for Mount Reneer communities. Unlike areas that experience regular earthquakes or seasonal hurricanes, the volcanic threat from Mount Reneer exists primarily in geological timescales. Most residents have never experienced a volcanic emergency. They lack the visceral understanding of volcanic dangers that comes from living through such events. Generational differences in risk perception reflect varying levels of connection to the mountain's geological history. Older residents who grew up hearing stories about Mount St. Helens express higher levels of concern about volcanic risks. Younger residents who moved to the area for economic opportunities often view the mountain primarily as a recreational amenity rather than a geological hazard. The emotional burden of living with constant awareness of catastrophic risk affects different people in different ways. Some residents report chronic anxiety about volcanic threats that interferes with their daily functioning. Others describe a fatalistic acceptance that allows them to enjoy their lives without constant worry. Most people fall somewhere between these extremes, experiencing occasional periods of concern that fade back into routine acceptance. The choice between fear and acceptance represents a fundamental human dilemma that extends far beyond volcanic hazards. Every person living in a high-risk area must decide how much mental energy to devote to preparing for disasters that may never occur. This decision involves weighing the psychological costs of constant vigilance against the potential benefits of emergency preparedness. The 2025 surveys show that 78% of residents in high-risk zones have never created an evacuation plan, despite being aware of the Lahar threat, revealing that knowledge alone cannot bridge the gap between understanding danger and taking concrete steps to survive it. This psychological disconnect between awareness and action becomes particularly troubling when viewed against the mounting scientific evidence that suggests the window for catastrophic failure may be closing faster than anyone previously imagined. Mount Reneer operates on geological timescales that compress human lifespans into mere moments. This isn't a question of if Mount Reneer will create another catastrophic Lahar. It's a question of when. The geological evidence, the monitoring data, the climate trends, and the population growth patterns all point to the same inescapable conclusion. We're living through the convergence of multiple risk factors that make a major Lahar event more likely now than at any point in recorded history. The USGS geological record shows approximately 60 major Lahars from Mount Reneer over the past 10,000 years. That creates an average interval of roughly 167 years between catastrophic mudflow events. The most recent significant Lahar occurred around 500 years ago with the electron mudflow. By statistical measures alone, another major Lahar is overdue. But statistics don't account for the accelerating factors that make the current situation more dangerous than any previous period in the mountain's history. The 2025 data reveals a mountain that's showing signs of increased activity across multiple measurement systems. The seismic monitoring network has detected earthquake swarms that suggest changes in the volcanic system's internal pressure. The thermal sensors show temperature increases in areas where volcanic gases emerge. The GPS stations measure ground deformation that indicates fluid movement beneath the surface. Each of these indicators might be explained away individually, but together they paint a picture of a volcanic system that's becoming more active. The glacial monitoring provides equally concerning evidence. Mount Rainier's ice masses are retreating at unprecedented rates, with some glaciers losing volume at twice the historical average. The glaciers aren't just shrinking gradually. They're developing internal fractures and weak points that make them susceptible to sudden collapse. Computer models project that Mount Reneer could lose 60 to 80% of its glacial ice within the next 30 to 50 years, creating conditions where massive amounts of ice could destabilize with minimal additional disturbance. The population growth in high-risk areas has created a human catastrophe waiting to happen. Over 180,000 people now live in zones that would be directly impacted by a major Lahar. These aren't scattered rural communities that could be evacuated easily. They're densely populated suburban areas with complex infrastructure, schools, hospitals, and businesses. The evacuation modeling shows that current transportation networks can't handle the volume of people who would need to flee simultaneously. The infrastructure vulnerabilities multiply the potential impact beyond the immediate destruction zone. The highways, railroads, ports, and power grid that serve the entire Pacific Northwest pass through areas that would be heavily damaged by Lahars. A single mudflow event could trigger economic disruption, affecting millions of people across multiple states. The cascading effects would take decades to fully resolve. The psychological disconnect between scientific warnings and public preparedness creates additional danger. Most residents in high-risk areas acknowledge the threat, but haven't taken concrete steps to protect themselves. They continue making long-term investments in communities that could be destroyed with minimal warning. The gap between awareness and action represents a critical vulnerability that could cost thousands of lives. The historical precedent shows that Mount Reneer has been producing major Lahars for thousands of years. The Osceola mudflow 5,600 years ago demonstrates the mountain's capacity for landscape-altering destruction. The electron mudflow 500 years ago shows that catastrophic events can occur even during periods of relatively low volcanic activity. Mount Reneer is behaving as it has over the last 500,000 years, suggesting that the volcano will continue to erupt, grow, and collapse in predictable cycles. The monitoring technology that provides unprecedented insight into the mountain's behavior also reveals the limitations of current warning systems. The instruments can detect changes in volcanic activity, but they can't predict exactly when those changes will lead to catastrophic events. The time between detection and disaster could be measured in hours rather than days or weeks. The gap between scientific capability and emergency response requirements represents a fundamental vulnerability in the region's disaster preparedness. The economic factors that drive continued development in high-risk areas create a feedback loop that increases vulnerability over time. Property values in these communities remain stable because most people don't fully accept the magnitude of the threat. Banks continue financing mortgages in Lahar zones. Businesses continue investing in infrastructure that could be destroyed. The economic incentives that encourage growth in dangerous areas operate much faster than the geological processes that create the danger. The emergency response planning represents significant improvements over previous capabilities, but the fundamental mathematics of mass evacuation remain unchanged. Moving 180,000 people through limited road networks in minimal time requires perfect coordination and immediate compliance with evacuation orders. The behavioral research shows that people don't respond to emergency warnings with the speed and consistency that evacuation models assume. The gap between theoretical plans and practical reality could trap thousands of people in the path of advancing mudflows. The stakes for current and future generations couldn't be higher. The communities built on ancient Lahar deposits represent investments of millions of families who chose these areas for their quality of life, economic opportunities, and natural beauty. The children growing up in these communities deserve to inherit a world where their safety doesn't depend on the continued dormancy of a volcanic system that has been producing catastrophic mudflows for millennia. According to USGS assessments, another major Lahar is likely in coming centuries, with leading volcanologists estimating a 10 to 15% chance of a major Lahar event within the next 30 years. The convergence of increased volcanic activity, accelerated glacial instability, growing population density, and inadequate evacuation infrastructure creates a perfect storm of conditions that didn't exist during previous periods in Mount Rainier's geological history. The mountain continues its ancient patterns, but the human elements surrounding it have changed dramatically. The 2025 data reveals something unprecedented about Mount Reneer. We're facing a catastrophic natural disaster scenario that could affect hundreds of thousands of people. Yet 78% of residents in high-risk zones don't have evacuation plans. The mountain's glaciers are melting faster than projected. The seismic activity is increasing. The population keeps growing in danger zones. All the warning signs point to a disaster that could happen tomorrow or in 30 years, but will almost certainly happen. If you live anywhere near Mount Reneer, you can check the official USGS hazard maps online to see if your address falls within a Lahar zone. Make an evacuation plan now, because this beautiful mountain that looks so peaceful on postcards is preparing to remind us that nature doesn't care about our sense of security. Lahars pose the top hazard at Mount Reneer, and immediate personal preparedness using verified evacuation resources could mean the difference between life and death when the mountain finally breaks its centuries-long silence.